people like, well, you don't have to do that. Just
Yeah.
act natural, man.
Just act natural.
I think they get right in the mind.
You about ready?
I am rolling.
All right, go ahead, Corey. Go ahead and run it. We'll leave the optional stop on this time. Just get ready with the feed hold button this first time through. Watch it real close. We want to make sure the clearance plane is where we want it. We'll change the tool to. Go ahead, cycle start. Just going to drill the 2 dowel holes. A little bit of coolant inside those holes makes a world of difference. Cycle start, yeah, go to tool 3. There we go.
We thought about it, we could have made a finish pass on there and just...
Yeah. Corey, go ahead and kick that feed rate up on this tool. Override your feed rate up to about 50% more. That's good. You can read your feed rate override, how much it's overridden on your data. It'll tell you exactly how much you can override your feed rate's overridden. It's 121%.
Yeah.
So you can see exactly how much you've overridden the feed rate. And we go to the fourth tool, we want to crank it back down to 100%. Cycle start. Okay, bump your feed rate back to 100%. Good job. You can also see your spindle load. That green line on the control tells you exactly how much the spindle load you're actually using.
Oh, yeah.
So if it gets up in the red, you know what you can actually tell by looking at that tool to tool every time you run the part, and if that the spindle load goes up, what's that telling you? If you run next time and that spindle load goes up higher with that particular tool, what's it telling you?
Getting dull.
Tool's getting dull, exactly. It's time to watch it. Cycle start. That counter bore.
Makes it cool down a little bit. It's taking just a little down.
The tool pressure alone will do that. And like you said, when the part cools a little bit, it'll do it.
Yeah. A rag.
That brush.
Look how
Yeah.
pretty it is.
Kyle, go ahead and take the calipers and check a couple diameters in those holes. Verify the 1/4 inch diameter. Let Kyle get in there and check the diameter of those holes. I want to know that big diameter, the counterbore diameter. How big is that? How big is it supposed to be?
On the money.
All right.
Counterboard.
Can he do that again and then he turn around towards me and talk to you?
Okay, check it again.
Wait a second, Kyle. Kind of move more to your right as you're doing it.
So he can see you doing it. You open the door all the way up.
There you go.
Slide this one all the way forward too, Kyle. Open that one all the way up. There you go.
Okay, now Kyle, lean back. Now lean in and do what you're doing. I'm sorry, I was zoomed the wrong way. Can you do it one more time? And kind of drop your right arm a little bit.
Right arm.
You don't have to drop it out, but just lower it a little bit. Okay.
$750?
Yep.
Round a button.
That's on the money.
Okay,
Yeah.
do it one more time, Kyle. Just like you did.
Perfect. Round the money. Check the quarter-inch dowel hole as well. Yeah. That'll be the, what is it? 250. Round the button. That's
Yep.
good. That drill goes right on size. It's a beautiful thing. Check the corner diameter holes as well, the clearance holes. What are they supposed to be?
Right here, 406.
426.
426. We used to have bigger drills. 1/64th bigger.
Yeah, that's why.
That's right. That's why. Good.
That's good.
Exactly what we want. Very good. All right. What you do is take it out, and I want you.
Okay, go ahead.
What we've done is just ran.
I'm gonna
Oh,
got the light
okay.
in the wrong area anyway.
Okay. Shut up. Who asked you?
Look at that.
I'm gonna get it on this side so I can get a little light on them.
Okay. All right.
Stand by. Okay, now we're going.
My name is Ken Milliman. I'm the manufacturing technology instructor here at OSU Okmulgee, and I teach all the manufacturing courses. These are my students. We've just run a part today for a robotics part, and we've run it on the NC machine, Cincinnati 750, and what they're going to do now is check and verify the dimensions are correct by the drawing.
And then one other question, Ken, step back around here now. What kind of career opportunities are there for kids that do this kind of work?
When the students leave this program, they'll be qualified to set up and run most pieces of NC equipment. We have a very different types of NC machines in this lab, and they'll be qualified to set up and run them, as well as with very little training, most any piece of NC equipment the industry uses today. We try and keep the most up-to-date machines as we can to have the same equipment that they're using in the industry today, so that the children are working on the same equipment the industry is. When they're also be qualified to do NC programming using the Spree programming or MasterCam. There'll also be Versa in SolidWorks and AutoCAD. They'll also be able to do a little bit of the maintenance on the machines. And we also do automated manufacturing techniques. We talked about flexible manufacturing systems, routings, some tool design, pretty much every facet of the manufacturing world from start to finish. They start running conventional machines to learn chip control, and from there they learn all the way up to run the big NC machines they're running today. When they get done, they'll be qualified to work pretty much anywhere in industry and manufacturing.
Maybe kind of point to something to talk about that.
This drawing that they made here actually was drawn by one of our students on the AutoCAD systems, and it's a one of a kind item that we wanted to make, so we made our own drawing, and we used that drawing to actually write the NC program to actually run the machine.
Raise it back up a little more. Okay, now put it down there and measure it. Okay, do it one more time. Now I'm going to focus on the gauge. If you turn it, go on and turn it around just like you did. Okay, and do your thing. Okay. Go ahead.
Yeah, you do it. You can do it without that.
Hopefully it's in the same spot.
Oh, what did it do? Did it go down?
No.
What did it say? The pennant error? You gotta shut it down.
Oh, okay.
These in that way you can see us take it apart and then put the part we made on. Whenever you're ready.
I'm willing.
Oh, okay. So we'll take this apart.
3/8/16 holes, right?
Yeah, I believe, yeah.
All right, just put these two in the corners. Are you putting all back together?
Well, we're not there. We'll take that apart now.
Take those and put these in each of the corners. Just put two of them when you put that on.
Those are too big. Yeah, by looking at them. See the thread? What we'll do is this is the part that we replaced. We replaced all that with this that we just made.
Those should be 3/8/16.
I think it's a work right here because I looked and the O-rings are down below these, so we won't never have air up here on top.
These aren't through. They're 7/16.
Put this back together.
Well, as long as those cylinders don't pop up,
Yeah, that's the only deal. If it's
it's not going to hurt it, but it'll.
It shouldn't, because that's why that lip is counterbored on that one spot.
I may have some
You
different
got some
bolts
air
down
now.
here.
Put some air on here and test it out. Oh, it's behind me? Oh, okay, I'm sorry, buddy. Be aware.
Yeah, see?
Yep.
It's taking too much air.
It's going to push up. Yeah, we're going to have to put washers or...
And what are y'all trying to do here?
What we did was this motor here was ran with this joystick, which actually sat on top of those buttons like this, and to move it you had to wiggle it back and forth to get that robot to work, and you couldn't get it to go just one way or the other because every time you pushed it you pushed multiple buttons and it would sometimes it'd get stuck. So what we did was we took this off and we marked all the holes and everything, and then built this piece to where if you wanted to go left, or it'd actually be like this, up or down or left or right, that way you were not pushing multiple buttons. You single them out by pushing them one by one. Washers or I thought that's all we need. 2 or 3 washers to keep it. He's got some, it'll work.
He's getting an automatic set.
Those are kind of cool.
Well, yeah, they are, but they're not. They'll work to prove out the theory anyway before we get carried away with it. Just grab a set of Kyle. Second drawer down the bottom box.
The big box, yeah.
Yeah.
Looks-
Either one below it or one above it.
We think those are a quarter.
Yeah. See if it leaks or not.
Let's go with theory number 1. Come on, baby.
Ooh, cool.
Got a little bit of leak on there.
No, that's right. Watch your hand, Willie.
Not quite working in it, dude.
Leaking too much air.
Yeah.
Put the old one back on top and we'll just show Rex how thing normally works.
That's the hard part, is getting it to go.
Well, that was the whole reason for the redesign is so that you could do it without manipulating it so that
Okay, do it again.
control, isn't it?
Yeah, that's the hard part of trying to get it. There we go. Let's try to get it to go. There we go. Working on that.
It's hard to... They had a capstone project, I believe this is made for, Rex, I think, you know, when, several years ago, I guess.
2003.
Oh, there's 2003. And it works okay, but the lever is extremely difficult to work either up or down or left or right. So we redesigned, made the drawing for the new block, we machined it, and now that was the point, we tried to put it together, and somehow our redesign didn't work, we got to figure out why.
That's R&D.
Yep, that's R&D.
Research and development, huh?
Yep. You get it just right, you can do it, but it takes practice to be able to get it so that you can make it go either up or down or left and right. But we're in the process of designing a flexible manufacturing system, actually going on the internet and finding equipment that will work to run a part complete using robotics, conveyors, automatic inspection equipment.
Slow motion.
Slow motion, you're getting pretty good. Let Kyle try. You try.
Yeah, bad, buddy.
It's hard to get the touch just to make it do one thing at a time.
Yeah,
you
real
can
slow.
do it, but it's, you push a button up, down, left, right, and that's it. That's the plan anyway.
We could get it to work a little bit faster, be pretty cool. Heat thrower.
Yeah.
I'm rolling and just kind of go through it all. Okay, I'm rolling.
All right. This is one of our capstone projects that we come up with. Chevron has done a lot to us with donation-wise. This is pretty much 90% donation from Chevron. I'm just going to walk you through the steps of this project. Here we got our actual holding tank for our water. This is the beginning of the process. This is, and the water comes out of the bottom, flows to this pump. And what we got one of these pressure indicator devices here. What it does is it reads pressure, PSI, the water going through it. This red deal right here is our control valve. It's actually going to control the water flow. It's going to have a restriction through the pipe here. And we got actually another pressure indicator on the other side here. And that's pretty much it.
Well, it's actually, let's tell them what it is. I mean, it's a simulated glycol contactor system.
Right.
And the plan is there will be a glycol contactor sitting here. It's on its way now. We haven't gotten it yet. That's the last component to this system. And it'll basically be the most visual part of the system where the water that we have going through the surge tank, through the flow control valve, into this scrubber here, will eventually make it back into the contactor and pour through the contactor and give them some a visual indication of how that process works. And you'll see the water in relation to air. We're running an air stream through here to show you the description of how the bubbler caps actually operate in the contactor itself. And the instrumentation, describe an instrument loop. You know, let's go through the logical process of how the instrument loop's reading, in this case, pressure, and then what do we do with that pressure? Say we want to control this valve.
Okay.
We can walk through how that system works.
What happens is we actually apply 24 volts to this, and out of that 24 volts, if we get a 4 to 20 milliamp signal out of it, whatever this pressure transmitter reads, it produces it as a 4 to 20 milliamp, and so we scale it to there. We set our lowest pressure rating to 4 milliamps, and then our highest setting to 20 milliamps, and that all gets sent back to our panel over here. You want to start talking about the panel here?
And this is basically the brains of the system. This is going to take all the process inputs from the end devices They're going to come in here, and Ryan and the other team members are going to take those signals and logically apply them to outputs. Basically, they're going to develop code in this brain to handle the control of those end devices.
Yeah, this is what's called a PLC. This is where all the computer part comes into play. That pressure indicator device over there, which runs all the way up here into this what's called an analog card. And this analog card, once again, puts a 4 to 20. It reads a 4 to 20 milliamp signal, and that converts it into computer terms of what we can read on this PC over here. And so the wire from the PLC goes all the way with this cable here, runs to the back of the PC, and then that's where we can communicate with our what the device is reading from here on the screen.
So I don't know how well you can see this display screen, but basically this is a graphical representation of what this process here will look like when they're finished assembling it. And what this gives them the capability to do is see all the instruments that they placed on that process in real time on this computer screen. And not only can they see them, they can trend them, they can database them, they can use all those measurements and all that information and store it so that they can maintain records of how the process has been and what it looks like now and compare them.
Okay, I'm rolling again. Just tell us what you were starting to say. This is a representation of that.
Okay. Basically, this is a computer system, and in industry terms, we call this an HMI. And basically what it is a graphical representation of the actual process. When that process construction is complete, it'll look very similar to this graphical representation. What that enables us to do is look at the instruments and look at the control loops in real time from anywhere, basically. If you network this particular PC, you can see it from any location. So that's the benefits of this structure. There's a programming software that Ryan and his other students have used to configure the PLC to talk to this HMI system. And this is a representation of what some of that ladder logic looks like, and that's what it's called. And this is actually the code that controls the process. So what they do is they say, well, this is the process. We got this loop. We know we want to control a loop this way. And they go in here and they build the logic to facilitate that. Once that's built, they take the data from that machine, which is a PLC, and via a communication cable, transmit that data into the HMI, which is right here. And they can do everything from here that they need to. They can control it, and they can monitor it, they can start it, and stop it. It's fully functional representation of what's actually happening with the process.
And this could be 100 miles away, and this HMI system can be 100 miles away, and we can have radio communications to communicate the two pieces together. So the operators can sit in a nice, comfortable, air conditioning place and control the operation out in the field. So that's what's really good for these HMI systems to work.
Have you talked about that?
Oh, so squat down?
Yeah, that'd be fine.
Okay.
Stand by. Actually, stand up and then squat down.
Okay.
Okay, I'm rolling.
This is right here is a control valve. This is where we can restrict the water that's going through this pipe. What we do to communicate to the PLC is we send this I to P, which sends its current to pressure. What it does is we send a 4 to 20, like we said, with the pressure indicator through this box, and this box converts it to 3 to 15 psi. To open this valve, it takes 15 psi to open, and 3 pounds to close it. So what we do is this thing, we send a 4 to 20 to it, it converts it to 3 to 15, and then it operates this control valve right here.
Good. Okay, let's start again. This time you're talking to him.
Okay. This tank right here is this, we'll actually hold water in it, but actually it's a simulated process that we use. They use different types of chemicals out in the field, but it's not safe and everything. So we turn to H2O, which is pretty easy to use because it's convenient. But this is just going to be a simulated process. We're actually going to pump water through this the contactor and stuff like that. pretty much is all it's going to be is just a visualization process. It's actually not going to work, but it's just going to show you how it all works.
You're excited.
This is a tank that we have in our process that holds H2O, which in the field they actually use certain types of chemicals like glycol. So this is actually not going to work as what you see out in the field, but it's going to give you a visualization of how it all works. So the water.
Go ahead.
You're getting better.
So the water runs through the bottom of the tank, actually flows through this pump here, and this into this pipe, which it's going to come back and into this contractor that we're going to be receiving here pretty soon. Sure.
Talk about the red thing.
This right here is a control valve. It actually restricts the flow of water through here, so we can actually get a constant flow through our system here. It's going to be controlled by this IDP, which is going to send a 4 to 20 to it. We're going to send out a 3 to 15 pounds, and this box is going to translate that for us.
Good. Well, start over there and go over there.
Okay. What we got here is our two pressure indicators here, one on each side of this control valve. These are actually going to control the pressure, or actually going to show the pressure through the pipeline. And this is going to control the water flow through it using a control valve, which is going to be controlled by that IDP over there. This little black thing here is what's called a scrubber. It actually takes the air, which got a mix of moisture in it. It's going to come through this system here, and it's going to come out drier on the top through some filters through the scrubber here.
Okay, Is he? Okay. He's going to go down, turn around, and come back this way to take off?
No.
Taking a video of it?
Yeah.
Okay. This guy's killing it. Who's this guy?
They don't see these type of plane brands on their airport very often. What I was talking about, videotaping, explaining the project. But I mean, that was worse than
Yeah, right when they go between you and cross the line between me and them and you. Now, go ahead and wait. Oh, you got to start